There have been many space missions that have pushed the boundaries of what our species can actually achieve. However, do you know how it is possible to travel hundreds of millions of kilometers to Mars? Landing people on the moon? Sending robots to Mars? Spaceships? If you actually consider the sheer distance traveled and the true complexity of each mission, you wonder, how is this even possible? In this video, we will answer this very question and truly understand how incredible missions like these are achievable. Let's get straight into it. In our previous two videos, we covered how a rocket can ascend to space and how it can reach orbit. These are the hardest first steps to any space mission. So now that we are in space orbiting the Earth, we need to figure out how to actually get anywhere. To go to any celestial body in space, many different maneuvers are required, meaning if we want to know how to get to places such as the Moon or Mars, we need to know how to fly in space. Let's first discuss how to change direction. A car uses a steering wheel to change the angle of its wheels, changing the direction it is going. A rocket, on the other hand, cannot use a steering wheel as the tyres are not touching any solid ground. Like rockets need thrust to speed up and slow down, rockets need thrust to change direction. RCS, or a reaction control system, is what does this. You can add small thrusters to each side of your spacecraft, just like this real image shows here, that when activated in certain ways, can change the direction your spacecraft is facing, in every single angle. This can also be used as multi-directional thrusters that can make you go forwards, backwards, and side to side. RCS especially comes in handy when docking to other spacecraft, as you can adjust the spacecraft in every way while wasting almost no fuel. As engines are simply too powerful and large to make tiny but important changes to your velocity, RCS thrusters are the way to go. Many rockets such as the SpaceX Dragon, Soyuz, and the now retired Space Shuttle all use RCS. Another way of changing your direction, this time without spending any fuel, is with reaction wheels. Reaction wheels are small electric motors that use power to spin at very fast speeds that change the direction your rocket is facing. This cannot influence your actual speed or trajectory, however. Both of these methods are useful in different scenarios and missions in space. Now that we know how to steer and change our speed in tiny amounts, we must know how to accelerate and decelerate on the level of changing our speed to reach other planets and moons. Before we can get high enough to reach other celestial bodies, we must know how to go higher and further in space in general. Your first instinct when orbiting the Earth may be just to fire your engines facing straight up relative to the Earth, as this should make your orbit higher. However, this isn't exactly the case. You focus so much on building up completely vertical velocity that your horizontal velocity diminishes, meaning while you partially go higher, you will fall right back down to the Earth. Rockets instead use a more efficient strategy. This is what essentially every rocket that wishes to go further in space first does. This is when you continue to accelerate in the same direction you are going, which is currently horizontally relative to the Earth. But why would you continue to burn in the same direction? Just like how we can go from space to orbit by extending our trajectory from a thin arc that will fall back down to the Earth to a complete circle, if we keep burning, our orbit becomes more of an oval with one side of it having a point a lot higher than the other. By continuing to increase our horizontal velocity, the Earth struggles more and more to pull on us, leading to our furthest point that our rocket reaches, or our apogee, becoming a lot higher. The best time to increase your orbit is at your lowest point, or periapsis, as your actions influence the opposite side of your orbit. This is the most efficient place to burn from. This maneuver is called the Oberth effect, and it is crucial for getting your orbit higher in the most efficient way possible. However, while we get really high on one side of our orbit, we descend to our original height on the other side. To not let this happen, you need to burn horizontally once at your apogee to extend your perigee, or lowest point, to an equal height of your apogee. This makes your orbit fully circular, meaning you always stay at the same height you intended to. Now that we know how to get into a higher orbit, we need to know how to get to other celestial bodies. We'll start with the easiest celestial body to get to, but still very challenging, the Earth's one and only moon, the Moon. The very creative and well thought out name given to the Earth's one and only natural satellite. The Moon orbits at a height of around 384,400 kilometers above sea level. For comparison, a GEO sits at around 35,000 kilometers above sea level. The Moon is very far from Earth, and is quite the challenge for our species to conquer. While we are talking about much bigger distances here, the same concepts still apply. We essentially need to raise our apogee to the height that the moon orbits at the exact right time so that our rocket intercepts the moon on our orbital path. Our orbital path needs to cross the moon's sphere of influence, or SOI. An SOI is an invisible sphere around a celestial body where its gravity is so strong on you that it is pulling on you more than the body you are currently orbiting. A path when you go through the SOI of a celestial body is called an encounter. We'll use the moon and Earth for examples. Unfortunately, once you are on course to encounter the moon, the challenge is not over yet. When you enter the SOI, you have a small opportunity to enter a moon orbit. If you do nothing, however, and continue on your current trajectory, you will fly by the moon and be slingshotted out into deep space. Once at the moon's perigee, or the lowest point you will reach while in the moon's SOI, you must burn in the exact opposite direction to which you are travelling. This makes you slow down. If you slow down enough before you exit the SOI, the moon's gravity will be strong enough to make you orbit it, meaning your rocket is now orbiting the moon. To land, you need to slow down even more so the moon's gravity can pull you down to the surface. These concepts go the same for other celestial bodies like Mars, just on a much larger scale, as this time you must first go so fast that the Earth's gravity can't pull on you at all and you exit its SOI. You then need to raise your apogee, or highest point, around the Sun to Mars's orbit to encounter it. The main two things you need to do to get to other planets and moons is, to put it as simply as possible, you have to go fast, and you have to have good timing. Missions such as the Apollo mission sending humans to the moon and back, rover missions to Mars, probes to Jupiter and Saturn, and even probes that travel interstellar distances are no easy task. But achieving a new milestone has never been easy in all of human history, and never will be easy. However, our species and our incredible brains, minds, and engineering skills have proven time and time again that we are capable of anything. And with the little steps we're taking to colonize the stars, who knows where we'll be and what we'll be capable of in the future.